Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be continue to go over the kinetics of radioactive decay, focusing on the integrated rate law. So let's get into this. So in a previous video I went over integrated rate laws with respect to chemical reactions and concentrations. You may have learned about that in your chemistry class. Your professor or teacher may have gone over that. If not, go back and review that. Go back and watch my video on integrated rate laws. But just as a little reminder, this is the formula. So this formula right here is the formula for the first order integrated rate law of chemical reactions given in concentration. So if you look, it's the natural log ln of the concentration of your whatever your reactant is at time t divided by the original starting concentration that you have, and that's going to be equal to the negative of the rate constant multiplied by time, whatever the time is at that particular moment that you're measuring. So this is for chemical reactions involving concentrations, but since we're not dealing with concentrations, we're dealing with just a substance, number of atoms. We're in nuclear decay. We're going to be dealing with number of atoms. So all we need to do is just replace concentrations with number of atoms or nuclides. So here it's the natural log of the number of atoms you have at that time t divided by the number of atoms you started with, the amount of your original sample, is equal to, again, the negative of the rate constant divided by t, or multiplied by t, excuse me. Now, keep in mind that you also know the half-life. So the half-life is T1/2 is equal to 0.693 over the K, which is the rate constant. So when you're solving problems, you can use this equation along with this equation. You can manipulate this equation and what's what I'm looking for? You can kind of change the form of it using algebra. And so you can transform this equation from this form to this form. This is the same equation. You've just done some manipulation of it and rearrangement of the parts. And so here you get the number of atoms you started with in your original sample, or I'm sorry, at time t, is equal to the amount that you had originally. So the number of atoms you had originally multiplied by e raised to the negative kt. So you can use this equation along with this equation here to solve for your problem. So if you're given, let's say you're given a certain amount of a substance, right? So I'm given certain milligrams of a radioactive substance, and I know I'm given the half-life, and I want to know how much of that substance is left after a certain amount of time, right? Here I have my amount after the certain amount of time, which is what the problem is asking for, or it could be asking for. So I have to be given the original amount, and I need to know what K, and I need to know the time that they're specifying that they want to know the amount of at that time. But notice in this equation, I need to know what K is. So I would have to use my half-life equation here and solve for K. So I need to be given the half-life. So if I'm given the half-life, I can solve this for K, like shown here. So I can solve this for K, plug in the half-life, and notice also I want to bring up that 0.693 comes from the natural log of 2. So that's where this number comes from. So K is equal to the natural log of 2 divided by the half-life. And so if I know the half-life, I plug that in, I find K, and then all I have to do is just plug that into this equation along with the other information I'm given, and then I can solve for the amount that's left after a certain amount of time, whatever t is. So that's one way to go about it. So you can do it in a two-step process. So solve for k first, plug k in, and then solve for the amount left over. But there's another way you could do that. So one of the things you could do is you can solve for k here and just substitute this in for k. So then what I do is I take this equation and I take k and I substitute this in, the ln of 2 over the half-life in for k, and I get this. So then now I don't have k involved here. And then what you do is you can do some algebra and manipulation. I'm not going to go through all of it. If you're interested in me going through all the steps and how you go from here to here, then let me know down in the comments, and I'll make a video showing that. But I'll show a little bit here. So here I have the ln of 2 over the half-life substituted in for k. And so then if I rearrange this a little bit, I'll have negative ln of 2 over t 1/2, which is the half-life, the amount of time that elapsed, divided by the half-life that's given. And then if I take the natural log, if I raise the natural log to the power of, or as a power of e, then the e and the natural log will cancel out. And then what I end up getting is nt over n naught, or n0, equal to 0.5, which is 1/2. That's where the negative ln of 2 after you do the manipulation. So again, I'm not going to go through that, but if you want me to go through it, let me know down in the comment section. And then you get, so this becomes 0.1/2, and then this goes to the power of that. So what I end up getting from here is 0.5 raised to the power of the fraction of the time divided by the half-life. And so then what I can do is I can multiply both sides by n sub 0, and then I get n sub t, the amount that I have left after time t, is equal to the original amount I had multiplied by 1/2 raised to the power of t over tf, the time that elapsed divided by the half-life. So I can use this equation. So if they give me the time that elapsed, right, that I'm interested in, and they give me the half-life, and I got to make sure that these two are in the same units. If they give me the time in years and the half-life is in minutes, then I got to make a conversion. I got to convert one of these so that both of them are in the same unit of time. So both have to be in years or minutes or weeks or whatever the case may be. So if I know the time that elapsed, and I know the half-life, and I know the original amount, then all I have to do is plug it into this equation, and it'll give me the amount left over after that particular time. So this is a one-step equation. I can do it all in one step if I'm given all this information, or I can do it in two steps. I can solve for k, and then plug k in for this equation, this equation here, and then solve this equation. So either way is fine. It's whatever you would like to do. But I do want to bring your attention to this equation here that I got to in my process of getting to this equation. This is a good equation to remember too, because this gives you the fractional amount. So sometimes a problem will be asking you what fraction of the substance is left after a certain amount of time. Well, this is the fractional amount. So if you use this equation, if they give you the time that elapsed and the half-life, then all you need to do is plug this into this equation, and it will give you the fractional amount left over. Also, one more thing, sometimes the problems will ask you for the percent left over. Well, that's just the fractional amount multiplied by 100. So that's what I have here. So if you take the fractional amount that you solved here, multiply by 100, that's going to give you the percent left over. So these are a few equations that can be very helpful for whatever the problem is asking for. So in the next part of this video, I'm going to go over, well, what if I have rates? Can I put rates into my equation and just use the rates if I have rates? Well, that's coming up in just a moment. Okay, so back to the rate of decay. So previously we were talking about how we can use this equation to find the amount of a substance left over from the original amount. But what if we could use the rate of decay instead and look at how the rate of decay changes over time? And so we know that the rate of decay is linearly proportional to the number of nuclei. Since the half-life is constant, we know that this is true. So since the number of nuclei is proportional to the rate of decay in the sample, therefore the initial rate, which I am writing here as rate sub zero or rate naught, right? So the initial rate and the rate at any particular time that I'm interested in can then be used in the integrated rate law. So here I show you here what I'm talking about. So I know that from the rate law, I have rate at a particular time t is going to be equal to the rate constant multiplied by the number of isotopes or the number of nuclei I have at time t. And then the rate of decay at time zero at the initial rate of decay is going to be equal to the rate constant multiplied by the original sample or the original amount that I started with. Okay, so then if I rearrange these, I get the amount at time t is equal to the rate at time t divided by the rate constant. And then the original amount is equal to the original rate divided by k. And if I do the one over the other, so I take the n sub t, the amount at time t divided by the amount initially started with, that's going to be equal to the rate at time t divided by k over the original rate divided by k. Well, the k's are the same. The rate constant doesn't change. It's constant, so that will cancel out. And so you get the ratio of the rate at time t over the original rate. So the amount at time t over the initial amount is equal to the rate at time t over the original initial rate. So I can take this and plug this into the original equation here. Since this is equal to this, I can just plug in the rates and deal with the rates instead of the amounts. So then I can use the integrated rate law, and all the equations I showed you before that involve the amounts, I can plug in the rates and I can do the problems with regard to rates. And I can see, okay, what I can calculate or I can determine what the rate is, what the new rate is at a particular time compared to what the original rate is or whatever the problem is looking for. And so that should be useful for a certain equation. So I can plug in rates instead of amounts, and I can do the same calculations. Okay, so the last thing I want to talk about, or at least point out, is that all of this can be used for radiometric dating, since the amount of substance is decaying consistently over time, and that the half-life doesn't change. We can then use this way, we can use these equations to determine the ages of certain things like fossils or artifacts that we find in the ground or in caves or wherever. We can then use that to date and find the ages of things. And so in my next video, I will go over radiometric dating. So thank you very much for your time. I hope this was helpful. I hope you found this interesting. If you did, then please like the video, share the video, subscribe to my channel, hit that notification bell. But when you do, make sure you hit the all button so that way you'll be notified by all my videos when I put them out. And finally, put a comment down in the comment section. Let me know what you think. If you've got a question, please ask. I love to answer questions. Thanks for joining me. Have a great day.